Hello, everyone. Welcome to AdTech Track at re:Invent 2021. How is everyone doing? Good, awesome. It's super exciting to welcome you all in person this year. My name is Ramesh Jetty. I'm a solutions architect with AWS. I'm joined today by my colleague, Orit Alou. She's a principal solutions architect based out of Israel. And we both work with customers who are focused on advertising and marketing industry, and we help build solutions at scale using big data and machine learning technologies. Predicting consumer behavior is critical for brands to really engage with their customers. There are a variety of use cases where these predictions can be helpful. Specifically with marketing and advertising industry, you would use these predictions to predict brand affinity, to identify how close the customers are to the brands, to identify what the preferred products are, and also to measure the campaign performance, to identify how effectively brands can spend their marketing dollars. But this can be very tricky based on the availability of known data sets, especially if there are a number of governance and rules and regulations that surround how this data can be utilized, especially known data. So in today's session, you will hear from two of our customers, Acxiom and AppsFlyer, on how they built platforms at scale to predict consumer behavior. You will hear a number of stories on how they leveraged SageMaker to build these platforms, and the lessons learned along the way. So to kick this off, I would like to first invite onto stage from Acxiom, Raj Srinivasan, Senior Director of Engineering. Raj.
Good afternoon, everyone. How's everyone doing? Is everyone enjoying the re:Invent? Good, good. My name is Raj Srinivasan. I'm a Senior Director of Engineering at Acxiom. In today's talk, you'll hear how Acxiom built a scalable machine learning infrastructure to build and score 5,000 audience propensity models and to generate 3 trillion inferences using Amazon SageMaker. In terms of agenda, I'll start with an introduction to Acxiom, who we are, what our core product offerings are. I'll give a high-level overview of the audience propensities product, which will set the foundation for the scaling problem we encountered in the on-premise setup, and the rationale behind why we decided to move to cloud, why we chose SageMaker, how we iterated on our architecture, and I'll wrap it up with some key lessons learned and some takeaways that will be beneficial for you all and the broader AWS community. Let's dive in. Acxiom is a customer intelligence company. We offer data-driven solutions and technical expertise to help businesses and our clients deliver exceptional customer experiences every day, which in turn powers their business growth. We do this by combining data, technology, ethics, and ideas. Acxiom is a well-recognized brand in the AdTech MarTech space. Our products and solutions are built with data ethics, privacy, and regulations in mind. We partner with brands all over the world, helping them in their customer experience journey. For example, our reach spans across 2.5 billion connected consumers. We have coverage in 60+ countries and have expertise managing 20 billion+ customer records. Being a premier player in the AdTech MarTech space, Acxiom has a diverse suite of product offerings that spans across identity, data, customer intelligence platform, digital marketing solutions, analytics, and strategy. While our suite of products is fairly exhaustive, in today's talk, we'll primarily focus on how Acxiom builds its high-quality data attributes at scale. And if you want to learn more about our products, refer to our website. A typical use case of Acxiom data is to use it in a marketing campaign to build a hyper-personalized messaging. Acxiom's core data assets, such as Infobase, which is our demographic data attributes, audience propensities, which is our consumer behavior and consumer interest attributes, and Personix, which is our pre-curated segments, can be combined to create and distribute precise audiences. our data spans across individual demographics, household characteristics, life events, channel preference, in-market timing, and many more. And clients and businesses can combine, mix and match these attributes to create a 360-degree view of their customers and prospects, but more importantly, deliver personalized messaging by understanding their needs, wants, and preferences. To take an example, a marketer looking to build a campaign can go really broad, that is, create messaging for all households in the United States, or he or she can go really granular to something like digitally oriented, male, 20-something, who have filled a prescription online in the last 12 months. Once these audiences are built out, they can be activated by using device IDs, mobile ad IDs, email, or other forms of identifiers. Demographics such as attributes such as age, income, gender, these are slow-moving or static. Whereas people's attitude towards brands, their preference for products, consumer trends, these evolve a lot more quickly. So any infrastructure that supports these consumer interest attributes or consumer behavior attributes has to be scalable and fungible enough to be able to capture these ever-evolving trends. So in rest of this presentation, we'll primarily focus on audience propensities product, which is Acxiom's consumer interest and consumer behavior attributes, and the infrastructure we built to support that, the machine learning infrastructure. Before I go into the infrastructure journey, I want to take a moment to introduce the audience propensities product. Audience propensities are nothing but probabilistic or model data attributes that are built by combining unique behavioral data sources with powerful predictive analytics. Proprietary data sources are combined with machine learning models to answer key questions that marketers are asking today. What products are my customers and prospects shopping? What channels do they prefer? Are they in market for my product? What content are they streaming and watching? And once these models are built out, they're projected onto a large universe comprising of 620 million plus records that provides marketers enough scale to customize their audiences. But why would marketers use model data? Why would they not go after known consumer behavior data? While known consumer behavior data will always be preferred, it has certain challenges. Known consumer behavior data is often proprietary, it's owned by the brand. Even if you can get hold of it, it's not available to need at scale. So with advancements in AI and ML, it has become increasingly viable to take smaller samples of available known consumer behavior data, model it out, project that onto a large universe, and this is a standard practice that is followed across the ad tech martech space. But another advantage of model data is that it produces a probability score as an output. So this gives marketers great flexibility at audience selection time, that is, they can optimize for precision or reach by going narrow or deeper in that probability score spectrum. So what differentiates Acxiom from our competitors is our large catalog of high quality and precise model data attributes, which is our audience propensities product, that spans across several industry verticals. For example, we have coverage across auto, insurance, finance, healthcare, CPG, technology, retail, and many more. Our clients use Acxiom data for a wide variety of use cases, such as developing insights and analysis, developing conquesting strategies to go after competitor market share, drive loyalty and retention efforts, create rich consumer personas, build real-time personalization applications, build predictive models, and lastly, drive marketing efficiency improvement efforts. All right, with that context, I want to dive into the architecture journey, but before that, I want to frame the problem by defining the issues we encountered in the on-premise setup. As of May 2020, all of Acxiom's audience propensity curation activity was happening in our on-premise data centers. Models were trained using open source tools or SaaS, and once the models were built out, it's projected onto models were scored on a large Hadoop cluster comprising of 13,000 plus cores. Acxiom has a catalog of 5,000 audience propensity models. Each of this model is scored on a universe comprising of 620 million records, so it generates basically 620 million propensity scores per model, for a total of 3 trillion propensity scores across all 5,000 models. And the data set on which this inference is run is 2 terabytes uncompressed, a fairly large data set. Now, this activity to score all these 5,000 models takes somewhere between 11 to 15 days on that large Hadoop cluster. Now, Axiom's can charge higher CPM in the marketplace for our data when our data, the models are the most predictive and the data is the freshest. So, this inference data set is refreshed every month. As a result, all these 5,000 models are rescored every month. So, this presented some challenges. This Hadoop cluster is a shared resource. It's not only used for scoring models, but it's also used for other business critical and data curation activities. So, by taking 11 to 15 days on this cluster, we were constantly impeding those activities. Further, this cluster was operating at its full capacity, and we could not really grow our portfolio. Scoring jobs on this cluster also required coordination with the cluster admin for scheduling and execution. Jobs will run for several hours and it can fail, so the engineers managing these jobs would have to constantly monitor and resubmit these jobs. So that added additional overhead. While we had a standard way to score models through the cluster, the training was done outside of this cluster using multiple homegrown tools. Each of this came with its own functionalities, but like each of them that created some inconsistencies, but also had limited support for the types of algorithms. And lastly, we did not have an end-to-end lifecycle management system that is needed to manage a portfolio of this scale. But a more important determining factor for us to move to cloud was due to the fact that this workload is the scoring, which is the most intensive part of the workload, is a spike resource demand workload. There is, on day 0 when we submit our jobs, we quickly ramp up, take 80 to 90% of our cluster capacity. And then once the scoring is done, we pretty much release all the resources. So this presented us with two options. If we need to shrink this timeline, we can either increase our on-premise hardware capacity or we can move to cloud. And when we did that assessment, we realized that we would need at least a 3x increase in our hardware capacity on-premise to achieve the SLA we wanted to hit. Whereas if we move to cloud, we can achieve the same goal by distributing the workload across multiple accounts or multiple AZs. We can also optimize for cost by using spot instances and other optimization strategies. So once we said, okay, we're going to move to cloud, we wanted to set some design criteria for the platform we wanted to build. We want to be able to score all 5,000 models inside a day. Why one day? In ad tech, speed is the name of the game. You need to be able to create the freshest data and get it in the hands of your clients as soon as possible. And our current time from the time when we get the raw data set to creating the inference data, scoring the models, and delivering to the client was an extended period of time. So we really wanted to shrink that. And so we set out a bold objective. Can we get this done in a day? As I mentioned before, on the on-premise, there was significant overhead to managing these jobs. So we wanted a seamless experience and a fully automated platform for model training, deployment, QA, inferencing. We also set a pretty high reliability goal, greater than 99% reliability and ability to recover on job failure. And because this is a platform that is demanding for a large amount of resources, we also needed to ensure that the capacity will be available to run these jobs. And we want to build an end-to-end lifecycle management system as part of this restack. And lastly, the cost has to be reasonable for both training and inferencing. So once these criteria were set, we started exploring the landscape of the tool, and we eventually landed with Amazon SageMaker primarily because of its robust IT and MLOps feature that spans across security, compliance, ML workflows, scalability, and orchestration. Amazon SageMaker, like any other organization, Axiom cares deeply about data security. Amazon SageMaker offers encryption in transit via TLS 1.2 encryption. It's PCI and HIPAA compliant. Amazon SageMaker makes it really easy to build end-to-end workflows. You can, it offers scalability both in terms of horizontal scalability and vertical scalability. You can pair it with any of the open source orchestration tools like Airflow or Kubeflow, or you can also use some of the native AWS services. And lastly, it's pay for use. You're not really logged into any licensing agreement and contracts, right? So this is these are the features that we really liked. So once we decided on Amazon SageMaker, we set out to build our machine learning platform on AWS, and we delivered our version 1 of the platform. We called this Axiom DaVinci in May 2021. Axiom DaVinci 1.2 comprises of two key pipelines. There's a training pipeline to score large number of to train large number of models at scale. And then there is a inference or scoring pipeline to score large number of models at scale. The training pipeline comprises of 5 key steps. There is once the raw data set is prepared, it's fed into a feature engineering step. This is where you would do feature preparation, imputation, one-hot encoding, and other feature preparation activities. Then you feed that into an optional data balancing step. This is to handle any imbalanced data classes in the data. And then there is a feature selection step. And Axiom data sets can have high dimensionality, so we do a pre-selection of features before we feed that into training and tuning. In the training step, we build models using multiple algorithms, and in the hyperparameter optimization step, we explore the parameter space of each of the algorithm using Bayesian search and build several candidate models. And in the model evaluation step, we look at some performance criteria to decide which candidate model to deploy. All of these capabilities came natively with SageMaker. It was fairly easy to stitch together into a pipeline. In fact, SageMaker offered us the flexibility to use the pre-built containers, as in the case of XGBoost or Linear Learner, or we could also bring our own containers, which we did in case of neural network using TensorFlow. Airflow, which is an open source orchestration tool, has all the needed SageMaker and Python operators to build that orchestration layer. In fact, majority of our effort was on the training pipeline was spent on figuring out how many models can we train concurrently and how do we load balance the resources. The DaVinci 1.2 inference pipeline comprises of 3 key steps. There is a pre-processing step. This is where you would read the raw data and filter to the specific features needed to score a model. There's an inference step to score the models and generate the raw proba values. And there is a post-processing step to take the raw proba values and scorecard and package that into the needed format for delivery. Since we use the pre-built containers for XGBoost and Linear Learner, our option in this case was to use SageMaker Batch Transform for inferencing. SageMaker Batch Transform is a purpose-built capability for running large-scale inferences. However, we couldn't accomplish the pre-processing and the post-processing step within the construct of the Batch Transform service. So we decided to supplement that with a Spark on AWS Glue solution. So the way this pipeline would work is you would read the data from S3, you would run a Spark on AWS Glue job to filter to specific features needed to score a given model, and you write that as an intermediate data set into S3, which will be read by the batch transform step to score the model. Once the batch transform step is complete, it will write the raw proba values as an intermediate data set into S3, which will again be read by the post-processing step for scorecarding and packaging, and then the final output is again written into S3. We stitched this into a pipeline and tested across all our algorithms to ensure this is functional. But once we started running full load tests, scoring several models at the exact same time, we started running into scale challenges. Given we had to score 5,000 models inside a day, we had to be able to score at least 200 models in a batch inside an hour to hit that one-day SLA. As we launched 200 models concurrently, what we realized was as each step finished, it was writing terabytes of intermediate data into S3, which has to be read by the subsequent step. So as a result, we were far exceeding the S3 prefixes rate limits for get and put. S3 was saying, slow down, I think you're writing too much data and you're reading too much data, and that impacted the pipeline speed. For Linear Learner, we used the pre-built containers, but the pre-built containers did not offer the proba values in the right format. It came in the JSON line format. All our data processing was in the CSV format. So we had to again read those data sets, do an in-memory merge to pull out the proba values, which again increased our memory and processing overhead. In the version of Airflow we used in our pipeline, variable speed queuing was not available. So each step of this pipeline was operating at different speeds. Pre-processing can be done a lot faster than inferencing. So ideally, you would want to do more of those, get it done, and wait for that resource to be available for inferencing. But since that wasn't an option, we had to set the parallelism at the overall pipeline level, which impacted the throughput and the SLA. To run 200 concurrent pre-processing and post-processing jobs, we needed a certain number of Glue workers, but our account level service quota was a lot lower than that. So we had to run each job with a fewer number of Glue workers, which again impacted how quickly that activity can be completed. And further, sufficient error handling was not in place to account for scenarios when resources weren't available, which again presented additional challenges. The batch transform was not built with enough instance diversity. So this, we took a couple of instances, optimized it, and assumed that we will get as many of these to score 200 models. But in reality, when there was spike demand for those instance types, we constantly encountered resource and availability issues. Batch transform has a rate limit of 1 transaction per second. At least when we were implementing this, that was the rate limit. But within our pipeline, there was no way to control several of the pre-processing jobs because we are running 200 models at the same time. There was no easy way to control several of these pre-processing jobs completing at the exact same moment and demanding for the batch transform resources. So this kind of manifested in a couple of different ways. On a more simplistic level, you'll just get throttled. You'll see an error saying, hey, resources aren't available. But on a more complicated level, because we're not running one batch, we're going to be running 24, 25 batches of these 200 models to score 5,000 models. If you're constantly exceeding that rate limit and hitting the SageMaker batch transform service, it could deem that like this is a DDoS attack and it can actually blacklist your account. So we really had to address this problem. So we introduced delays into the pipeline, we put some sleeps into it at various steps. We also implemented retries with exponential backoff. All of this, while it helped solve these problems, it really added additional delays into the processing. And lastly, max payload and concurrency are two parameters that we'll use to control the amount of data processed in the cluster. And this was kept to the lowest possible value for reliability's sake, but again, that led to suboptimal utilization of cluster. So with so many design flaws, it was really hard to make this pipeline work and make it score 200 models inside an hour. So we sort of learned some important lessons from this first iteration. Avoid unnecessary I/O operations and try to do as much of the processing in memory as possible. If for some reason you need to write large volumes of intermediate data, let's say for debugging purposes, then have a very well thought out and well-defined strategy for optimizing your I/O. Define appropriate S3 prefixing and data storage strategy, and pre-partition those S3 prefixes beforehand so that you can get maximum get and put throughput, right? Understand where you're going to be storing your input data, understand where you're going to be storing your output data, and make sure you pre-partition those prefixes. There's a really nice AWS blog on how to partition those prefixes, so refer to that for more details. But for large-scale data processing applications, if the S3 prefixing strategy is not defined correctly, then the available throughput is going to slow you down. Implement instance diversity in the type of instances you use, right? Use both multiple instances within the single job family, also try to use instances across multiple job families. Try to implement some sort of a round robin or a random selection. And if possible, if applicable for your use case, try to spread that across multiple AZs. For large-scale platform implementations, implementing a job control layer is absolute must. Pipelines that are operating at high scale, demanding large amount of resources, you need a piece of infrastructure that is observing all these events that are happening. Let's say, for example, there's a throttling event saying, hey, slow down, I think you are exceeding the rate limit. Or you encounter some error events where a resource is not available or memory is not sufficient, then you need a piece of infra that is observing this and able to take the necessary course of action. Repartition, pre-partition your input data sets to avoid any unintentional data skews. Managing memory is going to be extremely critical in these large-scale implementations. Understand what data is needed to do that specific job, only read those specific features or columns into your data set. These things may not matter in small scale, but will become critical as you scale up. So with these learnings, we decided to re-architect our pipeline, and we launched the version 2.0 of our inference pipeline, and we call this Axiom DaVinci 2.2. It launched in October 2021. In 2.0, we took care of all the basics. We pre-partitioned the input and the output S3 prefixes so that we are getting the maximum get and put throughput. We pre-partitioned our data sets to avoid any unintentional data skews. We implemented enough instance diversity by using several instances within the instance family as well as across different instance families. We implemented a round robin selection. We optimized the payload and the max concurrency for each of the instances used in the pool. But regardless of that, there was a big elephant in the room. We're still writing large volumes of intermediate data, which was really hard to get around. So we decided to move away from SageMaker batch transform because that is what led us to that design, and pivot to SageMaker processing. Now, SageMaker processing is a purpose-built capability that lets you run pre-processing, inferencing, and post-processing, all three workload in a single managed infrastructure. Each unit of SageMaker processing will read the data once, perform all 3 activities, and write the data once it is done. So this was a massive improvement to the reliability and performance. But there was a minor side effect to using SageMaker processing. The reason we landed with batch transform was it was compatible with the AWS pre-built containers. So for our XGBoost and linear learner containers, we had to rewire those using open source sklearn version to be compatible with SageMaker processing. Again, a very small cost to pay for the reliability and performance improvements we got, especially when we are scoring hundreds and hundreds of models. We also implemented a DynamoDB-based job control layer. This job control layer orchestrated and managed all the rate limits and SageMaker TPS requirement. It also increased the reliability significantly. So in terms of performance improvement, we saw a 73% reduction in inference time. From V1 to V2, we saw a 61% reduction in cost, a 98% reduction in S3 API request, and a 25% improvement in CPU utilization. So V2 was a huge success, and we were able to, on load test, we were able to run all our trillion inferences within our given SLA. So to wrap up, when you're building large-scale platforms, conduct proof of concepts with multiple design patterns, and before you arrive at your end state solution. AWS services function like Lego blocks, and you need to test out against multiple patterns and with reasonable load before you decide on which design to go after. Leverage AWS offered well-architected review sessions to vet out your design, because these guys have worked across multiple customer implementations, so the solution architects and the product leads will know what the common pitfalls are, and they can point out those before you put it into production. Be aware of your account level service quota before you finalize your design choice, because that's going to influence whether you want to build this in a single account or a multi-account. Build a job control for complex data processing strategy to orchestrate and manage your service rate limits, and have clear success measures around both your product and platform. And lastly, try to test your platform at full scale in dev before you put it into production. We took a month to actually prepare a dummy data set that we scaled it up, and we were able to run full workloads in dev. So that was extremely crucial. As we started to uncover issues, it was very easy to open the hood and see where things were going wrong. So to wrap up, when we started out, Axiom was in an on-premise setup on an infrastructure that would not scale. We are in a fully scalable machine learning infrastructure on Amazon SageMaker, has significantly reduced our heavy lifting. Our costs are low. We can refresh our models as frequently as we want. We have significant agility, and there's standardization among our user base. In future, we want to, in 2022, we want to look into multi-account deployment, incorporate some of the newer features, drive improvement to our model management capability, and also look into incremental learning and auto retraining. That's all I have for today. Thank you all for listening in. Really appreciate the opportunity. And next up is Benjamin from AppsFlyer, and I'll be available later on in case if you have any questions. Thank you all.
Thank you, Raj. Thank you, AWS, for having us here, and thank you all for coming in. My name is Benjamin. I am a senior software engineer at AppsFlyer. I started my journey with AppsFlyer 5 years ago, and for the past 2 years, I've been working with the predictive analytics team. I'm here today to present several LTV prediction solutions that we have developed using Amazon SageMaker, and our use of SageMaker developing a real-time multi-tenant machine learning solution for SKAdNetwork, Apple's new attribution protocol introduced with iOS 14. And nearing the end of my talk, I would try to provide some insights on the challenges that we faced, the solutions that we applied, and some lessons learned. AppsFlyer is the world's leading mobile measurement and attribution platform, with more than 1,000 employees across 19 offices, and with over 65% in mobile measurement share. AppsFlyer is the most trusted name in mobile attribution. We're extremely proud of our customers, but the logos that are here aren't just for the brag. They're also a testament of the scale that we handle. We send and receive over 100 billion events every day. Our platform handles this data with the accuracy and the reliability that the world's largest brands expect. Data is at the core of our platform. We've invested years in building and perfecting our measurement and attribution solutions. Using these solutions, our customers can measure user activity across multiple acquisition sources. They can connect to all their data and to more than 8,000 partners in our marketplace and make use of a wide range of solutions from audience segmentation to Protect 360, our mobile ad fraud solution. Our customer can analyze application performance with comprehensive analytics from lifetime value measurement to incrementality. For those of you who are not very familiar with the mobile advertising industry, a very short, simplified introduction to mobile user acquisition, or UA, the process of acquiring or essentially buying mobile users. This is done by advertisement in various sources, such as social media or advertisement in other applications or over the web. Each of these advertisement sources allows you to choose which audience or campaign you would like to target. The cost of an acquired user depends on the audience or the campaign that user belongs to. The assumption is certain groups or demographics are expected to produce better value over time than other groups. This value can be referred to as LTV, or lifetime value. LTV is the monetary or other value that the user is expected to produce over a course of a lifetime, which can usually be determined within 30 to 90 days of application usage. Although some campaigns are expected to produce better LTV, there is no guarantee that they will. Furthermore, those expected to be good campaigns will probably have higher acquisition costs, making the decision even harder. Should I invest in more expensive users in the hopes that they will justify their investment? Or perhaps I should invest in less expensive campaigns in the hopes of getting a better return of investment. So now I'm getting to the challenge that we sought to overcome. A UA manager will invest in several campaigns simultaneously, and he will wait. He will wait for a couple of weeks to go by. He'll inspect all the user data for all those campaigns, estimate the LTV of each campaign, and only then further acquisition can be done with some degree of confidence. Any decision at any given point in time will carry some LTV uncertainty. Our mission is to eliminate this uncertainty through early predictive insights. We want to provide our customers with an early prediction of campaign performance so they can optimize their UA without having to wait for long periods of time before identifying their best performing sources and campaigns. Product-wise, we wanted to provide our customers with an actionable ranking system that will allow them to identify their best performing campaigns and paint a clear picture on UA performance. Apart from providing a predicted LTV score, we would have to take into account acquisition cost, as any actionable benefit score should factor in both performance and cost. And lastly, the information should be available per UA source, campaign, and geo. From an engineering standpoint, when we initially approached this problem, we tried to map out all the challenges that we as service providers would face. Our mission is to not to create a single LTV prediction model, rather it is creating multiple LTV prediction models for multiple potential customers. The models should all be trained using only the data that originated from their target applications. But when it comes to feature engineering, we'll need to build generalized pipelines that can accommodate as many applications as possible while still making full use of all available data for each application. The pipeline should also be built for scale, as all the raw data from all the possible sources prior to filtering and transformation can weigh hundreds of gigabytes or several terabytes for just a few months of application usage. We also have to build a management solution that will allow us to effectively manage, inspect client models, move models to and from production, and integrate with other existing AppsFlyer solutions. We chose to implement our feature extraction pipelines using Apache Spark to effectively deal with the scale of the data. As to feature generalization, we initially focused on designing and creating temporal features, which describe the time relation between user actions, such as event recency or event frequency. We chose to initially create deep neural network LSTM models, as similar models produce good results in other AppsFlyer projects. The models were built using TensorFlow so that our data scientists can have full control of model specifics and are able to improve the models over time. We also created an internal experiment management and pipeline management systems. Amazon SageMaker does provide solutions for pipeline management and experiment management, and I strongly suggest checking them out. At that point of time, we did not see a need for real-time inference, and we were planning on using SageMaker's batch transform job as part of a scheduled flow. When training a model, we use raw application data that is stored on S3. We typically make use of 2 to 3 months of historical application data. We found this to be a good balance point between having sufficient user data for a good generalization while still using relatively fresh data. The data is filtered, transformed, and shaped using Spark, and is stored back to S3, standardized, and ready for machine learning. Right after that, a SageMaker train job is invoked using the pre-processed data from the previous step. The initial job will use boilerplate hyperparameters that we found to be a good starting point for most models. After the model is trained, it is evaluated using previously unseen user data. If an improvement in our evaluation metric is required, the results aren't good enough, we will launch a hyperparameter tuning job, and I will elaborate on that shortly. Otherwise, if we meet the target metric, the train job will be marked as successful. Either way, Amazon SageMaker will save any trained model to S3 alongside any artifacts that were used as part of the training when the train job is complete. That is also true for models that are created during the hyperparameter tuning job. The final evaluation of results is always performed by people, and the results are shared with our customers. This is crucial for trust. Our customers need to have a clear picture of model performance, strengths, and weaknesses. Our deep neural network models output ordinal predictions, but the accuracy is inspected using several numeric and categorical evaluation metrics. I know data scientists like having precise numbers when it comes to target metric evaluation, so this is an actual onboarding report of one of our customers. You can see all the metrics. All the targets in this report are in the scale of 1 to 9, 1 being the lowest score and 9 being the highest. I previously mentioned hyperparameter tuning with SageMaker. SageMaker includes an automatic hyperparameter tuning job, which can use both random search or Bayesian search. For us, the early stopping capability, the automatic stopping of tune jobs that don't perform as well as other parallel jobs is quite useful. Our models are relatively heavy, thus time-consuming, and this saves us time and reduces cost. In the chart that you are seeing, the red and orange graphs jobs are stopped automatically after about 50 epochs, while the better performing green and blue jobs continue tuning and improving the target evaluation metrics. Our models usually see an improvement of about 6% in our evaluation metric after the tune job is complete. Once training is done, we're ready to move on to our prediction flow. A scheduled prediction flow we initially planned on resembled our train flow. Using recent user data also accessible on S3, a Spark feature extraction job is performed, and right after, a SageMaker batch transform job is invoked. When that is done, inference results were saved back to S3. In the end of the flow, the results were uploaded from S3 to a managed RDS database and became available for dashboard ingestion. For scheduled prediction flows, using the batch transform job is definitely cost-effective and saves the hassle of maintaining an endpoint. We schedule these flows using AppsFlyer's internal Airflow so that we can schedule them accordingly to other jobs that might have needed to precede our job. And so we started onboarding customers for a minimum viable product stage. This is a screenshot of the MVP dashboard as it was available to our customers. Using this dashboard, customers could compare campaign performance, inspect each campaign LTV components, and use the insights to optimize. We're happy with what we achieved, and we're planning future development and improvements. Everything was almost ready for launching our product. But then something else happened. Apple has announced iOS 14. With it, iOS 14 brought a new attribution protocol, SKAd Network, or SKAN. With SKAN, IDFA, Apple's advertising identifier, which was used throughout the industry for identifying users, was deprecated. User activity measurement was also restricted. By default, SKAN lets you measure a journey of 24 to 48 hours from install to post-install activity. And the measurement must be delivered via the SKAN protocol, submitted from the user's device before a timer expires. Finally, both UA data and the measurement data are delivered via one aggregated postback. Just one postback that contains both the UA data and one conversion value for measurement. For us as mobile users, this is a great improvement in user privacy. But this is also an enormous challenge for an industry that was used to having all user data at any given point of time. And for us in the predictive analytics team, this also presented a great opportunity. If we can create an accurate prediction of the user's LTV and use that prediction as the value that is submitted to SKAN, we can provide our customers with a powerful tool that helps them efficiently optimize their UA performance within SKAN constraints. Instead of just providing a limited measurement of user activity, we will provide an accurate prediction of user monetization, retention, and engagement performance. We did, however, need to make some adjustments in our existing plans. In order for the solution to work well, it has to be done in real time, so that any user action that is performed even just moments before the user is required to submit the conversion value is taken into account. When we started planning our real-time solution, we knew in advance that we would like to make use of DynamoDB for storing user actions and events prior to inference. DynamoDB is highly scalable, it's fast, reliable, and its built-in support of TTL, time to live, is very convenient for us, as it allows us to keep all data for just longer than the available attribution window and not worry about cleaning it up later. DynamoDB will clean it up for us. Essentially, DynamoDB would act as a sort of a stream-to-batch transformer, aggregating all relevant data prior to and in between inferences. With that in mind, we then decided to build most of our flow using AWS managed components. This led us to the design that you can see on the screen. Events are consumed from several topics, Apache Kafka topics within AppsFlyer. Data is written to several DynamoDB tables. User metadata is also written to a separate table to be able to keep track of the user state. The data is also dispatched via SQS to Lambda. When Lambda is invoked, it loads all the relevant data from DynamoDB, performs the required feature engineering, and invokes the SageMaker Real-Time API. Finally, when the results return from the SageMaker Real-Time API, they're stored to yet another table, ready to be served to client devices. A client's device might request the value several times before submitting it, but it will only submit the last, most recent value that was returned. Finally, we'll receive all the postbacks, and we'll aggregate them, displaying them to our customers. This is a screenshot of the new dashboard that PredictSK users can see. On this dashboard, the user can compare all their campaigns in terms of performance. All groups are placed on an axis, where better performing campaigns are placed on the right side of the axis and are dyed green. Less good campaigns are placed on the left side of the axis and are dyed red, and average campaigns are placed in the middle. The size of each circle is the amount of users that that group or campaign has. Our customers can also inspect each campaign or group individually in order to get a better understanding of its LTV components and its acquisition cost. This product is currently in beta stage, and it is already used by several of AppsFlyer's customers, and we continue onboarding applications and customers as I'm speaking. Some stats on performance. For the real-time endpoint, The average inference time for deep neural network models is about 10 milliseconds. Inference times, of course, vary according to the scale of the data that is being used right now and the model type. Currently, we are not yet close to maximizing the potential throughput of the endpoint that we're using, and with several models in production, we're using a fraction of the available throughput. We're using a multi-model endpoint, and I will elaborate on that in a few slides. To train our models, we are using, on average, 5 GB of historical application data after filtering and standardization. The amount of data, of course, the amount of available data, of course, depends on the data that each application actually produces. Training deep neural network LSTM models takes a while, and with the scale of our data, it takes us about 35 minutes to complete a train job. Tune times are very similar to train times, apart from the jobs that will be automatically stopped by early stopping. The total length of a tune job, of course, depends on the amount of sequential executions that are launched. I'd like to share a few additional challenges and insights from our experience building these solutions, 4 takeaways on issues or insights we've encountered and thought that would be useful to share. The first one is regarding model performance. In the process of improving our model when working on the SKN solution, we had to introduce a lot of new data and features. Our deep neural network models were also refactored in order to be able to make optimal use of these features. When we started training our new and improved models, we saw that train times skyrocketed from approximately 15 minutes to 8.5 hours. That was completely unreasonable. Furthermore, performing a train job on a local machine using the same data and model took much less time. So we contacted AWS, and AWS asked us to share our debugger profiling report. In our debugger profiling report, we could clearly see that we were underutilizing GPU and overutilizing CPU. Eventually, the culprit was a bug in third-party software, but using the report allowed us to identify that we had a problem and gave us a lead to inspect. The SageMaker report also, the SageMaker profiling report also provides actionable messages that can allow you understand if all is functioning correctly and what can be done to improve your performance. The second takeaway is regarding multi-model endpoints. We're currently using a multi-model endpoint for multiple tenants, multiple client models for multiple customers on one endpoint. This provides us a significant cost reduction. Multi-model endpoints require that all models on a single endpoint be approximately of the same type and performance. There is also a cold start penalty. When you update an existing model, the first inference after the update will take significantly longer. For us, it's not very significant, as each model is expected to perform tens of thousands to hundreds of thousands of inferences in between updates. Some insights on visibility. Bugs and human errors are always expected when developing new software solutions. And the more complex and intricate your machine learning pipeline is, the probability of having issues increases. When designing our pipeline, we took the time to make sure that we log, save any piece of information that is relevant to our final outcome, whether it is transformation stats, data distributions, or copies of standardized and unstandardized data. I previously mentioned that we use DynamoDB as sort of a transient data source, and although it's very convenient for us, that also means that some data gets deleted, and this is hurting our visibility. To overcome this, we use the AWS Glue to export all the data from DynamoDB to S3, and that way we can always access the data and are able to inspect it at much lower cost. Exporting the data from DynamoDB to S3 does use DynamoDB's read capacity units. You can programmatically raise capacity before the export is done and lower it once you're finished. Either way, consuming this capacity only once when exporting to S3 is still more cost efficient than consuming this capacity every time you want to inspect the data. We used Amazon Glue Studio to create an ETL that exports the data from DynamoDB to S3. There are other ways to do it. For us, we chose to do it this way. And we used Glue Crawler to upload data to Athena for inspection and analysis. And last but not least, regarding time to production. I've not added time to production stats to the performance slides. It seems to me that time to production depends on too many variables, from team size to previous experience in similar projects. It's not that easily quantifiable. I do want to mention, though, that when we're faced with the challenge of creating a real-time solution in a relatively short period of time, much to our advantage, we had existing AppsFlyer expertise and infrastructure in processing large amounts of real-time data, and versatile, scalable, and reliable AWS solutions in SageMaker, SageMaker's batch transform job that allowed us to process large amounts of data loaded directly from S3 without any development overhead. Automatic model tuning improved our performance. Multi-model endpoints provide a significant cost reduction for keeping multiple models available for inference 24/7. And additional AWS managed solutions such as DynamoDB and Lambda that are easy to adopt and use, and they provide scalability and great performance. The combination of this existing AppsFlyer infrastructure, AWS solutions with some hard work and dedication allowed us to expedite our time to production for both our MVP and launching a beta product just in time for SKAd Network's release. If you want to learn more about SKAd, about Predict or Predict Escape, please visit us at appsflyer.com. If you have any questions for us, feel free to approach us after the session or contact us via email. And please complete the session survey. Thank you.